Hello everyone, my name is Ion Powell, and today I'll be giving a presentation on accelerating phase field-based microstructure evolution via surrogate models, in particular looking at LSTM-based architecture. Firstly, we'll be looking at spinodal decomposition, which is often a benchmark problem for looking at surrogate models for phase field modeling. It utilizes the Decomposition equation, which preserves a quantity, in this case is the concentration, and the inputs are the concentration and the phase mobilities. In particular, at the beginning, there's a completely stochastic at T0, and that's right before here. There's a completely stochastic distribution. And then both of the phases separate out over time. And the goal of this LSTM structure is to determine what the future steps are going to be. One thing to notice here in our Kohn-Hilliard equation is we have our change in concentration with respect to time related to the changes in spatial dimensions. This MC is essentially a combined mobility between the A phase and B phase, where it is a smooth interpolation. One thing to notice about our architecture is we start with the phase field model, and with these three inputs, we are able to generate the microstructures. We can take those microstructures and essentially do a Fourier transform using 2-point statistics, finding the distribution of the phases. Basically telling you how likely it is to find a certain phase at a certain location. You can take this right here and you can do a principal component analysis on it, and you have a reduced data space that can be trained into a machine learning model. In this case, we're using long short-term memory network, where we have these memory cells that are connected to one another. You see you have your previous long-term state and your short-term memory being passed on to the next cell. The inputs into this long short-term network are the principal components and these three original components here. We can see over here that the LSTM ends in a fully connected layer to help it come back into the needed components. And then the principal component predictions can be computed sequentially. These are the weights for the principal components. And this F right here is essentially the function for the LSTM. And we can see that sequential because we have A, the principal component weight, with K, the microstructure that we are looking at, I, which is which frame we're looking at. And we can see, and J is which principal component we're looking at. And we can see that each successive weight is dependent on every previous weight. So you can sequentially predict new weights. And here what's done is you take your stochastic model, you can run it through phase field to see what you get, but you can also run it through dimensionality reduction, put it into the LSTM that's been trained, you get this, and then you can reconstruct it. And the error is actually quite low, within 5%. 2-point statistics is a discrete fast Fourier transform that allows us to find different measures of the phase field model that help us understand how accurate it is. It was found here that 10 principal components can account for about 98% of the variance, so that's what the researchers chose to use. We can also see that here, this is a distribution over the entire plane, but you can take the average radial here, the radial average, and you can see at this dip right here, where the derivative is equal to 0, that's the feature size right here, this radius. And that's another thing we can use to see if our model is behaving appropriately. PCA does assume a linear reduction of the principal components, a mapping onto a linear space, but there are other techniques that can account for nonlinearity. It just so happens that spinodal decomposition works just fine with linearity. Now we will take a look at the LSTM architecture. For a quick review on sigmoid and tanh functions, the sigmoid function approaches 0 as the number becomes more negative, and approaches 1 when it becomes more positive, while the tanh goes from 1 and -1. What this allows us to do is construct different parts of the LSTM architecture. Here we have CT minus 1 and CT. This is our long-term memory. And then we have our hidden state, HT minus 1, and then HT that's passed on. That is our short-term memory. And this is our input, which in this case is the Fourier transform of the microstructure or the two-point statistics. You run this through a sigma. You run these through all these functions, right? And you have this sigmoid function right here that says it's the forget gate, because it can either be 1 or 0. If it's 0, it's telling it to forget this right here because this is multiplied in. So it can tell it to forget or to remember. Then here, it has a sigmoid function. So that's the input gate along with the tan H, and you create a new cell state, and that's added to the long term. So this is how the hidden layer with the short-term memory plus the input can impact the long-term memory. And then you come over here, there's another tan H function, so go positive or negative. In this case, to mention this, our A and B phase are denoted as 1 and -1. So the tan H function is essentially able to access that range and inform the model on whether or not it is an A or a B phase. This last part will have the long-term memory impact the short-term memory. There were 3 different error types looked at in this paper. The mean square error was what was actually used to train the model, but 2 other errors were looked at to confirm the validity of the model. There's the feature size error, and this is the feature size. That's the dip in the radial average that we discussed earlier. That's the minimum where the derivative is equal to 0. And we look and see how accurate that was. And we also have the Euclidean distance between every single point in that original map. With LSTM training, this is very interesting because more LSTM cells did not lead to better performance. It actually saw the best performance with 2 and 4 cells. In fact, the researchers chose to use 2 cells. And the reason why it worked better with less cells was because there wasn't enough data. There were only 5,000 microstructures generated over the course of 70 frames. Actually, that was 80 frames. And because of that lack of data, this is what worked better. In the same way that a deep learning network needs more data in order to perform better, this is the limit of how well this can be trained. And we can see the absolute relative error, which is what was used for that's ARE here, the feature size error. This was able to be reduced as more frames were trained. It was 90 frames that were trained here. My bad. It wasn't 70 or 80, it was 90. And the normalized distance, which is the Euclidean distance between the entirety of the Fourier transform. And we can see that reduced too. And we can also see here that as we predict frames, so our last frame that we trained on was 90, so this model was able to predict future frames, so 91, 92, 93. We can see that the error between them is really close, along with the normalized distance being very close too. That 5% target has been met for much of this. And we can see the matching between the predicted and true statistics for the radial average is very close. So there's a phase field recovery algorithm that is run on the Fourier transform of the microstructure that discretizes the recovery, and we can see that here. And then this is it plugged back into the phase field model to recover the shape. And we can see that the accuracy is very impressive here. In conclusion, a machine learning surrogate was trained on a large phase field dataset. The surrogate model produced accurate and rapid predictions of microstructure evolution in a low-dimensional representation. And this model can accelerate phase field predictions. In fact, it was about 42,000 times faster than using phase field alone. In the future, this can be used in more complicated phase field models. And future research has actually explored this. This is one of the benchmark papers that has been used to develop further projects. Thank you.